Hello, everyone. Welcome to this section on data structures and algorithms. This lecture is on heap data structure. At the completion of this lecture, we expect to cover what a priority queue is. Also, we'll define what a heap data structure is. Under that, we're going to look at max heap and min heaps. We will go further to look at implementing a heap data structure using linked data structure and one-dimensional array. And lastly, we will look at some areas where heap data structures could be applied. Let's start with priority queue. So a priority queue is an abstract data type that supports the following operations. First, if an insertion is to be performed on the queue, each of the elements must be associated with a priority. And for any element to be deleted from the queue, that element that must be deleted must have the highest priority. Now, what is the difference between the priority queues and the regular queue or the stack data structure? The main difference is that it's similar to both of them, but the main difference is that in priority queue, each element is associated with a certain priority. Now, if we want to implement priority queue using an array, and we first want to store it in a linear list. When we store it in a linear list, we need to have each of these elements associated with their corresponding priorities. Then the efficiency of inserting an element into a priority queue is of the order of 1, but the efficiency of removing an element from a priority queue is of the order of n. This is because when we want to perform this uh, deletion or removing an element from the queue, it requires us to search for the element within the list. And while performing the operation, we may end up searching through all the nodes before we can get the element that we are searching for. And that increases the efficiency to the order of n. So what do we do to reduce this efficiency or reduce the complexity? For us to increase the efficiency or improve the efficiency rather, we have to introduce the heap data structure. So a heap data structure is ordered binary tree, and is also a binary tree that is complete. You remember in the previous lecture, we introduced a complete binary tree. This binary tree, for instance, is complete. Rather, it is not, anyway, it's not full, but it is complete. It's not full because these leaf elements are missing, or it is complete because in all levels, starting from this level to the last level, all the levels are full, and all the levels or all the leaf nodes are full, starting from the left hand side towards to the right hand side. So for the max heap, so the max heap has this principle that all the elements at the root node must be greater than the elements at the or the children nodes. So if you have a look here, you see 66 is greater than 45, and 66 is also greater than 38. If we consider this sub 3, 38 is greater than 32, and it is greater than 12. So this implies that even the children node or the subroot must satisfy the heap properties. So the heap can be converted to mini heap. Sorry, the max heap can be converted to min heap. And what is the difference between the max heap and the min heap? The min heap is literally can be said to be the inverse of the max heap. This is because in a max heap, the root node is always the largest number, but in min heap, the root node is the smallest number. So if we convert this to min heap, we're going to have a structure that looks this way. If we go back to the previous slide, the minimum number is 3 and the largest number is 66. So we will now have to remove 66 and replace it with 3 because 3 is the minimum. And when we perform the operation, we have something that looks this way. This is the minimum or the min heap. However, we will see how we can perform the operation in subsequent slides. Now let's look at performing insertion in a heap. So the way to perform insertion is we can perform insertion following these steps. First, we have to insert the data that we want to put into the tree to the bottomless or the bottom leaf of the heap. So, and the insertion must be done to towards the left side of. I mean, we have to start from the hand side of the leaf node, and at times we might realize that the level is full and we need to move to another level in order to insert the element that we want to put into the binary tree. And on performing the insertion, we might also realize that the binary tree might deviate or destroy the heap property of that tree. So the element we inserted might destroy the heap property of that tree. And when that happens, we must have to perform a kind of restructuring operation to restore the tree to the heap property that it has lost. So how do we restore the tree? To restore the heap property, we when inserting, we have to move the data that we have inserted and move it up to the root or to a position where the element will be such that the parent will restore the property of the heap, they restore the heap property. And such operation is of the efficiency of the order of n. Now, we're going to discuss these steps in subsequent slides. And let's look at what we mean from what you have just said. Now, we want to insert an element 17. So where do we insert the element? Remember, we have to first of all consider if the element that we want to insert is, I mean, the space where we can insert the element. So first thing is that the element must be inserted at the lowest level, and this is the lowest level. So then the second thing is that we insert from the left towards to the right. So if we start from the left, being here, this is occupied, we move to the right, and the only space we can insert is this place. So this will be the position for us to insert this element 17. So now we have inserted, then the first question we need to confirm is that the first question we need to ask is to find out if the heap property is still maintained. Um, then yes, the heap property, sorry, the the tree is complete, is still complete, but the tree is not having the property of a max heap. This is because we have 70 at this point, and 70 is greater than this, is also greater than this, and greater than this. But heap property says that the highest number or the element with the highest value need to be at the root node. So we need to perform operation to ensure that this element being 70 is moved to the root node. And why until that is done, this structure has not restored the properties of a max heap. So our priority now is to move the 70. And how do we move the 70? We swap 70 with the parent node and consider these two elements. We swap again and consider these two elements. Then we get to the point where our operation is complete. So at this point, this tree has been restored to max heap, and the operation is going to end here. Then what is the efficiency for inserting in a heap? What is the efficiency? What do you think is the efficiency? Well, the efficiency is dependent on the height of these three. And because it's dependent on the height of these three, the operation is going to be just based on the height. And the efficiency is going to be the big O notation of the order of log n. Now, let's look at how we can remove an item from a heap. So in order to remove an item, so yes, we have to look and find the item with the highest priority. And the item with the highest priority is always the item at the root node. So in this case, the item that we need to delete or remove will be the one at the root node. And if we delete the item, we also have to perform operation, the kind of moving the subtrees to a point that the heap property is restored. Now let's use this as an example. So this is the heap, this binary tree that we have. So which of these nodes do you think is the right one to be removed? The right one to be removed is 66, which is the root node. The reason is because it's the one with highest priority as far for max heap. So if it is the min heap, then the minimum element will be the one at the top. So, but in this case, where we have the max heap, the element to be removed is the one with the highest priority, and 66 is the element with the highest priority. So what do we need to do at this point? We need to remove 66. And when we remove 66, we are now left with some complications. The complications are that the tree are separated, because on removing these, we have 45 subtree and 38 subtree. Another problem we will face is that we have to restructure this to restore it to max heap properties. So what do we do? The first thing we will do is to look for the node that can replace that node that we have removed. The reason we do not have to choose the node at the extreme left is that if we take this node at the extreme left, then this tree will not be complete anymore. But if we take the node at this point, then the tree will still be complete. The only thing we now need to do is to reorder the tree, to move the elements in the tree so that the tree will be restored to the max heap properties. So we replace 66 with the value 30, and now it is complete, but it is not a max heap. So the next is to make it a max heap. So how do we go about making it a max heap? Now, for us to make it a max heap, we have to perform some operations. And what kind of operation is that? We have to look at the root node and compare it with the children nodes. So at this point, we can realize that 45 is larger than 30, and at the same time, 38 is larger than 30. So how do we decide which one to swap with 30? Then for us to decide, we have to compare these two sub-root nodes. So the two sub-nodes are 45 and 38, and 45 is larger than 38. So we have to swap it with 30. So if we perform the operation, 30 will move to this place, and this side of the tree is completely settled. But at this point, this 30 is larger than 20, but it is smaller than 35. So we still need to perform an operation at this point in order to make the tree max heap. So we're going to swap 30 with 35. So this is what we're going to have. And at this point, we have restored the heap property of the tree after removing an element from that tree. Now, the question is, what is the efficiency for removing an element from a tree? So now, from what we have seen, we can also see that the efficiency for removing the element in this tree is of the order of log n. Now, if you compare it with the previous one, the priority that we had in either uh, slide 3 or thereabout, we remember that the priority at that the for removing an element is of the order of n. But in this case, we have the efficiency for removing an element in heap reducing to the order of log n. Okay, so at this point, we want to perform operation. We want to represent the heap using an array. So how do we represent this heap using an array? The best way to approach this is first approach them level by level. Then while approaching them level by level, you start from the left. What I mean is this. If we want to represent this element, these three in an array or using an array, we start with the root node. On the root node, you will only have, at this level, we only have 66. So we record 66. So the next element is going to be the element from the second level. And we start from the left. So the value is going to be 45. We record 45. Then the third it's going to be 38 because it's still on the same level. We record 38. Then we come down to the next level, which is the third level, and we have 20. So that's how we keep recording until we get to the last level. So these are called the indices of these elements. And if you look at this place, you see that this leaf node is missing. This and the other leaf node are also missing. And that is the reason we have these three spaces empty. So how do we index this? We can index these elements using their index number. In other words, I'm trying to say that we can identify these elements using their index number. So the index number for 66 is 1. So if you are writing a program, you can retrieve this 66 using the index. At the same time, for index number for 17 is 9. So likewise, others, you can use the same pattern to retrieve your data. Apart from having the index number from 1, we can also represent the use the index number to find the relationship between the parents and the children nodes. What I mean is you can find the relationship between these parents and the children, which are 45 and 38. So what this also means is that if we're given a root node, for instance, this node, and we don't know the value that's supposed to be here, but we have the indices provided for us. We can use the value of, we can use the index number of the parents node or the grandparents node, the parents node anyway, to find the value or the index number of the child node. Let's see what I'm trying to explain. So for instance, if you want to find the index number of the left child, that will be equal to the index number of the parent times 2. So we don't know the index number of this, which is the left child, but we know the index number of the parent child. So if we multiply the parent child by 2, we're going to have the index number of the left child node. Likewise, we can get the index number of the right child node by using the parents node, saying multiply the parents node by 2 and add 1 to 8. So if we multiply this by 2 and add 1, we're going to have 3. The same thing is applicable at this node. So if we have this sub 3 and we know that this node has the index number 3, we can multiply it by 2 and add 1 to it to get the index number for the node 12. So if we use that of the parents, we can find the index number of the parents using the child index number. If it could be directly or approximated. Approximated is, for instance, if we have to find the index number of this parent here, and the child is 6, the left uh, index child, the index number of the left child is 6. If we divide it by 2, we're going to have 3. But if we want to use the um, index number of the right child, then if we divide it 7 by 2, we're going to have 3.5. So you approximate by just using the value 3. So in some cases, we might want to, sorry, I mean, this also is performed or corresponds using the complete binary tree principles or properties. So in some cases, we might want to start the index from zero. And if we start the index from zero, then the pattern we followed in the previous process might not work. So we have to change the pattern to look like this. So the index value or number for the left child will be equal to the index number of the parents times 2 plus 1. So if we say 2 times 0 is 0 plus 1 is 1 here. Likewise, 2 times 1 is 2 plus 1 is, sorry, 2 times 1 is 2. Yes, I'm correct. Plus 1 is 3. So if you follow the same principle, you can get the parent and as well as the left, the right, the index number for the right child. Now we want to compare the AVL tree, display tree, and the max heap, looking at focusing at insertion and deletion. So for AVL tree, most of the time the efficiency is of the order of 1, and we perform rotation to restore the balance. And if we want to perform deletion, the efficiency is also of the order of 1, and we will perform rotation to restore the balance. But for split 3, the efficiency is always of the order of n, and you also perform the rotation to restore the element. And the same thing is applicable here. We perform rotation to restore the element to the best position, which is the root. Then on the heap is a bit different, because in the case of the heap, the first, the efficiency is of the order of log n. And what we do is that we do some swapping from the root. And if we want to do delete, if we want to delete any element, the efficiency is also of the order of n, and we swap to the bottom leaf. Now, if we compare again these data structures, focusing on some areas, we can see that the AVL tree is a binary search tree. And we perform operation which focuses at balance factor to restore the tree to the normal properties, to retain the AVL properties. But for that of splay is also a binary search tree. And most of the time, the focus is on the most recently visited nodes. And the heap is not really concerned or focusing on if the tree is binary or not. The heap is focusing on the if the tree is complete. So it's looking at complete binary tree, but it's not like looking at the search tree, whether it is a search tree or not. Then so it also focuses at the relationship between the parent and the children nodes. And most of the time it depends, the complexity depends on the height of the tree. Now, let's now look at implementing priority using priority queue using heap data structure. From the operations we have performed, and excuse me, we can say that the heap data structure provides an alternative method to implement priority queue. And this is because the height of the tree is the main concern. And the highest priority item is also the main concern of the operation. So in this case, the both the insertion and the removal operation is of the order of log n. Now, why are they with the efficiency rate at the order of log n? The efficiency is at the order of log n because we do not need to search through all the elements for us to perform the insertion or perform the deletion. So it only depends on the height of the tree. These are some areas where the priority queue, um, the heap data structure could be applied. So one is for implementing a priority queue. That's like using in Dijkstra algorithms, which is used to find the shortest path tree in a graph. This is not covered in the lecture, but it's available on the module. Another one is for Kruskal's algorithm, which is used to find the minimum spanning tree of a graph. It's also not covered in this teaching, but it's available on the module. And the third one is the Huffman's algorithm, which is used for compressing text. And another area where this heap data structure is used is for sorting algorithm, which is referred to as heap sort. This could be found in activity 10.4b. Now let's investigate how a heap data structure can be used for sorting algorithm. So for us to, okay, we have these and we are, you are advised to think about how a heap data structure can be used to sort a set of data. Then you can also use demonstrate this using a card. So let's have a look at some of the steps that you need to take. So for you to perform this operation, you first of all need to build a heap. In bracket, you can use Heapify. Then yes, the next step is to retrieve the root element. The root element is the largest element if it is a max heap, but it should be the smallest element if it is a main heap. So when you've retrieved the root element, and the next step is to swap the root element with the rightmost leaf on the bottom leaf. So you remember that if we want to perform the operation, we always move from the left to the right. Or in this case, we have to swap with the element at the rightmost. The reason for swapping with the element at the rightmost leaf is to ensure that at the end of our swapping, the tree will still be complete. Then we perform the sorting, then rebuild the heap without the previous root and continue the performing until we have the data sorted. So in this case, what do you think is going to be the efficiency for the heap sort? The efficiency for the heap sort is still of the order of log n. Now let's look at more activities. The first thing on the list of the activities is for us to draw all possible max heap containing the four values 1, 2, 3, 4. So now we can perform this by first assuming that this is the first element. And if we have the first element here, we now have to check if this is heap max, because there is no other element or child element to this root element, then we can say or assume that it is heap max. Then we move to the second element. We can add the second element to this place. So we have 2. But is this heap, is this max heap? No, it's not, because if you look at this, you see that 1 is not greater than 2. So we have to make it max heap by swapping. So we have 2 and 1 coming to this position. So now it is max heap. Then the third element is 3. And the only space where we can add this, because this level is not full yet, is at this place. So we have 3. Then we have to consider again, is it max heap? No, because 3 is greater than 2. So what we need to do, we have to swap. So when we swap, we have 3 at this point and 2 at this point, then 1 at this point. Then we go back and pick the next element, which is 4. Then where do we need to insert? Remember, for our insertion, we have to start from the leftmost, because if we add it here, then this 3 will not be complete anymore, or we want the tree to be complete. So we're going to add it here, and we have 4. So now the tree is complete, but is it max heap? No, it is not max heap. So what we need to do, we need to swap this and swap that. So when we perform that operation, we have 4 at the root node, we have 3 at the left child node, we have 2 at this point, and we have 1 at this location. So this is one of the possible um, structure of the max heap. I will leave the rest for you uh, to complete. Following these steps that we just followed here, you can draw other possible structures of the max heap. Okay. So the next question is it possible for search to search for a specified value in a heap? Do you think it is possible? I will I'll tell you what this will look like. I'll give you a clue. One thing you have to consider is it should be dependent on the kind of the heap. Is it max heaps or min heaps? So remember that in the max heap, the value at the root node is the value with the highest priority. But for the min heaps, the value at the root node is the smallest value, which also is the highest priority. So now, do you think that you can sort to find a specified value or data item? With this clue that I've given to you, I'd like you to try this and respond during the tutorial section what you think about this question. Then the last question here is for us to investigate how we could convert an array of data stored in as arbitrary order into a max heap. So how do we convert this array and store it into a max heap and convert it into a max heap? So I think another area we should be considering is this question, because we want the operation to be less than the time it takes to create the array. So the time it takes to create the max heap. So when we finish the operation, the efficiency should not be more than that um, of the efficiency we used when we are creating a max heap. Now let's have an example of what this can or how we can achieve this. So assuming this is the value of the array that we have, these are the elements. And if you look at these elements, you see that they are not ordered. So they are just arbitrary numbers. Then if we are to prepare a heap for this, we're going to have a structure that looks like this. So this structure is showing us that the first value is 4, the index 2 is 1, index 3 is 3, index 4 is 2, and the following the order till we get to index 10. Now, how do we make this? First is that this tree is complete, but it is not max heap. We are asked to make it max heap. And at the end of making it max heap, we should also ensure that our time is less than the time it takes to create the tree. So what do we do to do this? What we can do is to think less about the leaf nodes and consider the nodes first of all, consider the nodes after the leaf node or the level after the leaf nodes level. So what I mean is this. If we consider these levels, we realize that at this level, there's no leaf node attached to it. Then we go to the second level from the bottom up to the top. So the second level is this level. There's no leaf node attached to it as well. So we let it be. Likewise, this one. But 16 has a leaf node attached to it, which is 7. Then we have to perform an operation here. What kind of operation do we have to perform? The operation that will make this a max heap. Now, for making this a max heap, we already have 16 here, which is greater than 7. So we don't need to perform any further operation at this level. So the next operation we need to perform is we move to the left, consider this level, which has element 2. So for this element 2, we compare it with the children nodes. So the children nodes 2 is smaller than the children nodes. Then we need to move one of the children nodes to replace position of 2. So which one are we going to swap with 2? The one we are going to swap with 2 is the one with the largest value. And if you look at these two values, 14 and 8, 14 is the one with largest value. So we're going to swap 14 with 2. So we perform the operation, we have operation that looks this way. Then we are all done with this level. Then we'll move to the next level. So the next level is 3 and 2 and 1. So at this point, we compare 3 with the children nodes. So the children nodes are greater than 3. So one of them must have to replace the position of 3. And the one that we replace is 10. So we move 10, then we have this. So we have to move this, to get value that looks, structure that looks this way. So we now move to the next level, which is this one. We compare these two and realize that 16 should take the place because it's bigger. Then 16 we take here. And when 1 comes to this place, we can compare these two as well. Then 1 needs to come down, 7 needs to go up. So if we perform the operation, we have 1 here, 7 and 16. So we are done with this level. So the next level we're going to perform is the last level. So the last level we compare itself with the immediate children nodes, and the one with the largest number will take its place. So we're going to swap 4 with 16. So 4 is at this position now. When you compare it with the children nodes, we realize that 4 is smaller than 14 and 7. So we have to swap it with 14. And at this point, 4 is smaller than 8. So we need to swap it with 8. So lastly, we're going to have a max heap that looks like this. So finally, we now have a max heap, which is also complete. And this operation has reduced the complexity or the efficiency to the order of log n, y, which is less than the the time efficiency that we would have used to create the heap operation or heap tree. Now, this is just some areas that you need to cover in in this workshop. So we have some exercises for you to try your hands on, and also perform some uh, operations like being able to create and maintain a max heap or min heap. You can also try your hands on how to sort using heap sort. You can use the operations such as basic operations, determine their efficiency and also their best or worst case scenarios. So this is where we're going to end this section. Thank you so much and see you later. Bye.